We're starting 6.2 here, which is on the kernel and range of linear transformation. So first up, let's look at the kernel. We're going to define it, and then we're going to show how to find it. So if T is a linear transformation that maps V to W, then the set of all the vectors that get mapped onto the zero vector, that's called the kernel of T. And these vectors, they make up a subspace of V. So I want to look at a few examples. But when I wrote these, I tried to start with the easiest example, and I think that might not be the most instructive way to go. So let's start with example 103 here. T is a transformation that maps R2 to R2, and T of xy is x minus y, y minus x. Well, the kernel is the set of everything that gets mapped to 0, 0. So if we want to find the kernel of this thing, what we need to do is set x minus y equals 0, and y minus x equals 0. And we have to solve those simultaneously. We could put this into octave and solve it. It would be, so you've got x minus y equals 0. Then this is minus x plus y equals 0. If you put this in, this one's actually easy enough. We can do it quickly here. So that's our system of equations. And if we row reduce it, it's going to turn into this, because we're just adding the top and bottom together to get the new bottom equation. So this top line tells us that x has to be equal to y. So the kernel of T here is going to be, we can write it a couple of ways. The kernel is, it's the set of points x, x, where x is a real number. If you think about it, that's all the points that are on this line. So for instance, the point 1, 1 would get mapped to 0, 0. So would the point 2, 2. And if you add those together, you get 3, 3. So anyway, that's the kernel of this. This linear transformation, it operates on the plane, and it sends everything on that line to 0, 0. All right, let's look at 102 here. T maps R2 to R3, and notice what this rule says. Regardless of what x and y are, it always maps everything to the 0 vector. So the kernel of this would be all of R2. Because whatever you plug in, it's always going to take you to the 0 vector in R. All right, let's look at 101 now. This maps R3 to R2, and if the input is x, y, z, it gives us an x coordinate of x plus 10z and a y coordinate of 0. So for this, we have to have x plus 10z equals 0. So that means x has to be negative 10z. So this is going to be negative 10z. Y can be absolutely anything, and z can be anything. So points of this form where y and z are any real number, that's our kernel. I'm going to move this over because there's another way we could do this. Once we've got this equation up here, x plus 10z equals 0, it's only one equation, but you could still think of it kind of like being a, well, you could still think of it being a system of equations where you've got 1, 0, 10, 0. And then this thing's already in reduced row echelon form. So if we write it out as a system again, both of these guys are free variables because they don't have a leading 1. You get x is negative 10z, y is y, and z is z. So you could write this as XYZ is, I'm going to change the order here, y times 0, 1, 0, plus z times negative 10, 0, 1. So this is another way you could write the kernel of this thing. You could also say the kernel is the subspace with these two vectors as its basis. Now, this is more of the way that I've been doing things. Writing an answer out like this. The book tends to like these sorts of answers, and not only that, they tend to change it from y and z to like t and s for no good reason, really. So anyway, that's how you'd go about finding the kernel. Well, it's one method for finding the kernel. One thing you might notice here, if this looks familiar, we previously learned about the null space of a matrix. Null space and kernel are essentially the same thing. If T is a linear transformation defined by A times X, then the kernel of T and the null space of A are the same thing. It's just we use the term kernel when we're talking about it in relation to a linear transformation, and we use null space when we're talking about it in relation to a matrix. But they're the exact same thing. And in the next video, we're going to find the kernel of some more linear transformations. And the process we use is going to be exactly the same thing we used for finding the null space of a matrix. So we'll pick up there in the next video.